Little higher. Okay. Hello. 1, 2, 3, 4, 5. Yes, that's good. Yeah, I should be able to hear back what I'm saying. Thank you. Okay, good afternoon, everybody. My name is Shailesh Chandra, and I'll be going over content for transportation engineering. And broadly speaking, this lecture will cover these topics, and I'll try to touch upon the background for each of them, and we'll go each section one by one, and we'll have some practice problems for each of these sections. And then if you have any questions, you can you can keep noted down, and I'll answer as we go along. The basic purpose of this session is to also give you some tips how to score high in transportation engineering section. So I'll provide you some ways to remember some of the formulas and equations, and also how effectively you can use them during the actual exam time. Okay. So first topic is which we are going to cover is on geometric design of streets and highways, and then we have like sections A to H. So that's our first focus, and then we cover design of intersections. Then we'll have one problem on pavement system design, covering different thickness, subgrade, drainage, rehabilitation examples, and then we have traffic safety, traffic capacity, and all these in the sequence. Okay. Geometric design is a most important part of FE exam. I mean, you'll expect at least a good number of problems in the transportation engineering section from geometric design. So, so that's why I think this becomes very essential for you to kind of know the material before you appear for the test. So let me get started with the background for geometric design, and before I delve into the actual content of the design itself, we have to know some of the material from surveying. So I won't go into the depth of surveying. I'll just touch upon some of the important things which you need to solve problems from the surveying point of view, and also which get applicable for geometric design of different alignments like horizontal and vertical alignments. We'll go into details of geometric design exactly after this. So let's start with stationing and understand what exactly it is. And so the material here pretty much summarizes your stationing concept. Okay. So if you have something expressed as in feet, how to express that? Express the length measured in terms of stationing. Okay. So if you see, I don't want to go read all this content, but I just want to give you an example. So if you have, so look at this thing here. A stake placed 825 feet from station 0 plus 00 is labeled 8 plus 25. Okay. So let me just erase this part. Okay. Whatever. Let me just, yes. So a stake, read from here, a stake placed 825 feet from station 0 plus 00 is labeled 8 plus 25. Okay, which means that lengths are divided into 100 feet sections called stations. Okay, so this is a very good way to remember 100 feet. All right, just keep this 100 feet in your mind. Okay, so when we have stationing of that, you can convert that into corresponding length, or in meaning of length, you can convert that into corresponding stationing. Okay, so that's very essential. So if you have, say, maybe let's take another example here, which is right here. A stake placed 2,896 feet from a reference point. Okay, at station 10 plus 00 is labeled. I just want to get rid of this thing. Okay, this square is also. Okay, so a stake, I'm looking at this last two lines. Similarly, a stake placed 2,896 feet from a reference point at station 10 plus this is labeled 28 plus 96. Okay. Exactly. So you see this 28 times, well, 28 times 100 plus 96 gives you 2896 feet. Okay, so that's something which is you need to note down. Also remember for before we move into geometric design of vertical curves and horizontal curves. Okay. So again, takeaway is this 100 feet sections. Okay, keep that 100 feet in your mind. Okay, because NCES or FE exam doesn't give you these information, so you have to memorize this. There's no way out of this. All right. So after having done this, let's move on to our actual content on geometric design, and then we'll follow the material. Most of the pages that I'm skipping basically is covered in your plane surveying section, so I don't have to go into details. But I think there's another instructor who would provide you more information on the surveying part. So first of all, we touch upon geometric design, and we'll go over horizontal curves. And again, you have to memorize some of the things here. There's no shortcut, and there's nothing to kind of have it like from your experience. This has to be memorized. Like the terms which are mentioned here have to be memorized. What is PC? What is PI? What is PD? Okay. So in reference to this diagram that you see here for horizontal curve design, you must have seen some horizontal curves, like curve when you're driving a car. So essentially that's the sketch which is simplified here and then presented to you. Okay. So the first one is PC. Okay, it's a point of curvature, the point where the back tangent ends and the curve begins. So it's right here. Okay, that's PC. Okay, so in an exam question, you will have things like, okay, PC is this, or stationing of PC is this, stationing of PD is not known. How would you know the stationing of PD? So it won't tell you this is a point of curvature or a point of intersection or point of tangency. Okay, this you will have to know what they are on, how to put it on a diagram. And the good thing about geometric design is if you are good in geometry, that's some additional information. If you are good in geometry, you need not memorize any of the equations or formula. But if you are not, then there are some basic equations or formula which you need to know when you appear for the test. Okay, and we'll have some examples, and then you will kind of be able to relate to those. Okay, so don't get bogged down by so much of things that is contained in this figure here. Okay, it's all you need to know is this PC, PI, and PD, and rest of the terminologies are given to you here. Okay, it seems a lot of information, but most of the notations that are being used here are not in context to this diagram which is here on the right hand side. Okay, so for example, you don't have velocity here, you don't have vehicle speed here, you don't have all these terms here. The terms which you have here is M, which is middle ordinate, which you see right here. Okay, then you have LC, which is long chord, which is right here. Okay, so this is pretty much the entire chord that you have from here to here. Okay, then you have T, which is the tangent distance. Okay, so you could mark all of these here, okay, which you need to kind of build this sketch up. Okay, so that's something. So PC, PI, PD, they are all marked in this horizontal sketch. Okay, and the length of the curve is, okay, I need to get rid of this, some of the diagrams here. Okay, length of the curve is pretty much this entire thing right here. Okay, so in most of the horizontal designs or horizontal designs of curves, or the goal is to get this length. Okay, why? Because this is what you construct on ground. Okay, this is where actual construction is about. The rest of them are virtual points. For example, the center is a virtual point somewhere. You don't see it on ground. Okay, similarly, PI is something which you don't see it on ground. What you see is this red line which we draw, which could be a highway or freeway. Okay, so that's pretty much what the goal is of this entire geometric design. Okay, for horizontal curves. We'll also go to the vertical curves in a bit, but right now this is what we are focused on. Okay, so having gotten familiar with all these terminologies here, let's move on to some more content here and see what kind of questions do we expect in the test. Okay, so here's the first one, which I marked for reference. And again, so let's read this and see how quickly we can solve this, and what is a smart way of solving this without having to remember equations. So this is one of the questions which you don't need to remember formula here. Okay, but if you are good in geometry, you will easily able to relate to what the problem is asking. Okay, so the question is, what is the most nearly the curve length? Keep this in mind. This is the length we are designing for. Okay, this is what we actually look for as an answer to most of the horizontal designs of curves. Okay, so what is the most nearly the curve length of a horizontal curve with a radius of 2080 feet and an intersection angle of 60 degrees? Okay, so if you go back to the diagram here, this I, which is right here, and in this it's here. Basically, this is the intersection angle from here to here. Okay, so that's given to you as 60 degrees, and radius of 2080 feet is given to you. Okay, that means the entire length from here till here is given to you. So basically, this is a sector of a circle. Okay, this horizontal sketch of the horizontal curve. Okay, so if you know the principles of geometry, okay, is very quick to get to the answer. You have a curve like this. All it's saying is this is 60 degrees. Okay, and this length from here till here is 2080 feet. Okay. So how do we get the curve length? That means I'm looking for, let me go to this. I'm looking for the length from here to here. Okay. So in this, in any geometric principle that we have, without even going to the equation, okay, your first thing that you need to do is convert all the angles into radians. Okay, and that means this becomes 60 and divided by 180 degrees, okay, times pi. Okay, so okay, that's the first step that you always need to do is convert all your angles into degrees. Okay, so that's lesson number one. Okay, very basic thing that you need to do as you see this problem. Okay, once having done that, it is a law or maybe a rule in geometry that length of a curve like this, okay, the length from here to here, A to B, let's call A to B, is always equal to radius times, or radius of the sector of the circle times your theta. Okay, theta equals 60 degrees. Okay, expressed in radians. Okay, if you remember this, then you don't have to kind of really memorize the equation, and this comes from geometric principles. All right, so once you have this, all you do is convert this theta into radians, and that's what is being carried out here. Actually, r times I is your basically the theta. Okay, I think this pen is really okay, and that's what is further carried out. Okay, to 2080 times 60 degrees times pi over 180 degrees. Okay, times the radius, which is 2080. Okay, and then you get 2178.17 feet. So what do we do with